my students and teachers. Prof. Samuel Lee received a BS degree in electronics engineering from Kurpok National University, Daegu, South Korea in 1999. The MS and the PhD degrees in electronics engineering from Pohang, South Korea in 2001 and 2006 respectively. He is currently an associate professor with the School of Electronics Engineering, Konpok National University. His main research interests include cyber physical systems control, network control systems, nonlinear systems, fuzzy systems, robust control, model predictive control, and his industrial applications. Now let us welcome Samuel Lee, Prof.
Yeah, thank you for introducing me. Good afternoon, everyone. Can you see me?
Yeah.
Yeah. Okay, I will start my presentations. I will share my screen. Okay, can you see my the Windows screen?
Yeah.
Okay. Yeah. From now on, so if you have some questions, please send the chattings. I can check your question. I can answer. Okay, I will start my presentations. Okay. Yeah. Good afternoon, everyone. I'm Professor Sang-mun Lee in KNU, South Korea. Thank you for inviting me in these seminars and appreciating Professor Lee Hao giving an opportunity for international cooperation. In these times, I'm going to talk about new stabilization method for TS fuzzy system. In this works is based on my recent published papers, IEEE transaction fuzzy system and IEEE transaction neural network learning systems. So I have not enough time to prepare this presentation files. So please give me your understanding, even if there are some any typo and mistake in this presentation. Okay, the presentation content as follows. After I introduce my research areas of my interest and recent our lab project, and then I will explain the recent developed new method for TS fuzzy system. Finally, I will conclude the doors. It takes about 50 minutes. First of all, to help your understanding, I will introduce my research field. My major is control theory and applications. Especially my doctoral research topic is about model predictive control based on optimal control theory. Recently, I'm interested in cyber physical system to extend my research area. The detailed reason will be described in the follows. Also, I have studied about the stability analysis and controller design for fuzzy system in depth. Currently, I will try to combine the control theory and artificial intelligence technique using reinforcement learning. As you can see, so you can find my detailed research information in Publon's site, which is provided by Web of Science company. For a period of approximately 10 years or more, not many, but roughly 200 papers are published, thanks to the student and many research colleagues. Some papers was selected as a highly cited paper. That is selected by the Clarivate company, which is a Web of Science managing company. Thanks to that, I have been nominated as a highly cited researchers. That is top 1% researchers in the world from 2016 to 2020. I didn't know why I was selected as one of highly cited researchers. Recently, I found it from seeing this map as citing my article networks. The number is cited person's number. In these figures, the numbers refers to the number of the people citing the papers. As you can see in these pictures, there are many researchers who are doing similar research around the world. Particularly, many scholars in China are sharing the similar my research topics as shown. My papers are, these papers are my highly cited papers within the 10 years. Highly cited paper refers to the top 1% most cited paper in each research category, such as physics, mathematics, chemicals, engineering, in 23 research areas in Web of Science. When you look at the detailed keywords, you can find the topics as Pudgy and neural networks related. So this is because a lot of people have been interested in this field due to the recent development of the artificial intelligence. Also, so my research networks has a lot of the connections with the Chinese scholars, and this photo was taken 4 years ago in Dalian. When I attended the CCC, a Chinese Cultural Conference in Dalian, we can also see the pictures taken with Professor Yang in Northeastern University and Professor Bach in Yeungnam University. The picture on the right was taken after dinners with a Chinese scholar in my research group. Today's host, Professor Hao, was probably hiding in the second rows. Why did you hide in there? Here's like Professor Dan Ye, Hong Bing Zheng's, most of them are working as editors for top-class international journals. Before I explain my detailed research areas, to help your understanding my research field, I must first mention the Fourth Industrial Revolution. The Fourth Industrial Revolution is being prepared in Germany first, and each revolution is brought about by new technology. The first revolutions was driven by steam engine. The second one is the invention of electricity. The third one was led by the internet. So, what technology can the fourth industrial revolutions be explained? Most scholars say it is cyber-physical system. Unfortunately, many common people are not very familiar with what is CPS. Cyber-physical system is composed of cyber element and physical element. Cyber elements are described as computing, communication, and control. And physical elements include real objects such as robot and autonomous vehicle. Combining the two elements, CPS is the systematic integration of cyber function and a physical device or process. Recently, CPS technology has been applied to autonomous car first, and it will be expected that the next will be applied to the intelligent robot. Then this CPS technology needs the convergence of computing, communication, control. So I became interested in the following topic to study CPS from the point of view of control researchers. The first one's from the nature and the physical process, how to measure the state of the system using multi-sensor. The second topic is how to get the model of a cyber-physical system, which consists of continuous time and discrete time component. So it is not easy to describe the model. Third one is how to optimize the objective of control system design with constraint. Generally, we usually use some convex optimization technique. Introducing the result of my recent research conducted in my lab, it is a project on the external force estimation of robot manipulator. Robot manipulators are very popular in the industrial side as automation tool. Currently, only programmed position-based movement are repeatedly performed. In order to humans and cooperation with human and robot to work together in the futures, information about the force applied by the robot to the outside becomes very important. However, since the force sensor for measuring external force is very expensive, so it is difficult to install and use in the current system. Therefore, in this project, we developed and applied technologies to predict estimate the external force using sliding mode control method. This project was carried out during 10 months. And it was first tested in a virtual environment based on the robot OS system. Then applied to a real robot to quickly complete the project. In this way, the cyber-physical system have to shorten the development period. When we was in PhD course, it takes 1 year to prepare to set up the environment. But nowadays, we can very quickly develop this kind of system. As mentioned earlier, the modeling is the first and most important things to deal with the cyber-physical system. In order to control the robots, it was first necessary to obtain kinematics and dynamic model of complex robot, such as inertials and Coriolis force and gravity force. And the computer was programmed to understand the robot motion using mechanical engineering method. So detailed explanation will omit in here because of the short time. As shown in the right block diagram on the right, the external force is applied to the robots was calculated using information about the robot torque, input, and the output angle and angular velocities. As you can see, the force applied to the 7th joint is accurately predicted. So as you can see is the video, you can find the each 7 joint external pulse can be measured, not measured, estimated by using our technologies. With these technologies, if a robot lifts an object without any pulse sensors, it can automatically calculate its weight. So we can apply various fields. Based on the control series, we can estimate the various physical quantity without any sensors. The second case is application of control theory to autonomous mobile robot. In order to implement autonomous mobile robots, many sensors such as LiDAR, camera, encoders in the motor must be used. However, each sensor's sampling time is different. So, by using fusion of the sensors, these measurement data, we should to accurately know the state of the system to perform the nominal task. Therefore, in this project, we were able to accurately obtain the current position and speed of the mobile robot by designing the observer-based estimator for the system with multi-sampling times in each camera and encoders. So we can achieve the success project. Before applying it to the real systems, it is also, so we simulated it in the virtual environment and developed an algorithm that avoids obstacles using LiDAR. As you show in these videos, you can see the similar real systems. We can apply this in the virtual environment. This video is an experiment on the task of tracking given trajectories, and it shows that when using the proposed sensor fusions, tracking control is more improved than when using each sensor with only use encoder or only use camera. Encoder is easy to control the positions with fast sampling time, but there is a disadvantage that large errors occur when a slip occurs on the floor. Otherwise, the camera uses a technique called as visual odometry, which is easy to detect change in its own position, but has disadvantage in that it requires a lot of computations. So we combining two sensors, fusion techniques is applied in this project. So you can see the improved the trajectory performance, tracking performance. From now on, I will explain the recently developed control method for TS fuzzy systems. All systems are expressed as nonlinear systems, and in order to systematically deal with these nonlinear systems, there have been many studies on parameterized system, such as TS fuzzy or LPV system, linear parameter bearing systems, a long time ago. Such a parameterized system is expressed as a linear combination of the linear subsystem at each operating point. In this case, if you know the nonlinear functions, you can use the weighting function theta that is multiplied by it. Considering a joint robot as let's consider the examples as a single link robot with a flexible joint. That system is expressed as first order differential equations. In here, sine functions is included. This nonlinear function is expressed as a linear combination of the two linearized value b1 and b2 by using fuzzy logic. If these nonlinear functions are expressed as in two sectors in all areas, it will be analyzed as global sector nonlinearity. And if the sector condition is satisfied only the special section between from A to C, it should be analyzed as local sector nonlinears. The sine functions can be expressed as a parameterized system using membership function of fuzzy p variable between the sector 0 and 2 and analyzed as a global sector nonlinearity. It is called as Takaki-Sugeno fuzzy system. In our study, we focus on finding a systematic way to design the membership function dependent controller using these fuzzy membership functions. So, controller also is expressed as a linear combination of each control gain. Here, the control gain is expressed as a linear combination of each local controller in fuzzy logics. Like that. The aim of our study is to find a relaxed design condition for four topics of these parameterized nonlinear control system. The first one is to find the absolute stability condition that satisfy the sector constraint. The second one is relax the sampling time for sampled data to reduce the network burden of the network control system. The third one is to increase maximum delay time in the time delay system. The first one is to improve the H infinity performance to reduce the output norm against the disturbance. These four topics are in trade-off relations with each others, and improving one side degrade the other side. For example, if one want to the nonlinear sector increase, the infinity performance deteriorates. So many researchers are competing to improve the above problem with the benchmark problem. The purpose of this study is to develop the new design method which can outperform the previous result. Our research topics are largely divided into two categories. The one is design parameter-dependent controllers, as shown in this upper figure, for parameterized nonlinear system. The other one is design a parameter-dependent filter for estimating the state of the systems, which also is a parameter-dependent gain. There have been a lot of research on this topic in last decade. They can be grouped into three representative types related to our research work. The one is the use of parametric LMI technique, which was proposed in Afghanian in 2000 years. And recently, my research work was published in 2018 in IEEE transaction fuzzy system. The second method is to use modified fuzzy membership functions. Representatively, the imperfect premise matching method was proposed by H. Lambs is used. And performance is improved by using different membership function in original system and in the controller. The third one, there was studies to improve the time delay and sampled time by using new reaffirm function and integral inequality condition. So our main issue is how can use the information of the system be utilized under parameterized conditions, and how to derive the condition by constructing parameter-dependent reaffirm functions. Also, the main issue is how to obtain the parameter-dependent gain in the controller and estimator, how to deal with a synchronous sampling problem for the parameter as well. For the sampled data system, the main question is how to design a new reaffirm function that is sampling time dependent, and how to relax the upper bound condition of the integral inequalities. In our studies, the system was developed while guaranteeing the stability based on the reaffirm function, and the problem was formulated using the linear matrix inequality techniques. All design variables are expressed in form of a convex function to ensure global optimization. So our approach have advantage. The advantage of our approach is that the simulation can prove the given problem without any experiment. To apply the proposed method, we proposed the new Pinceler lemma. The first equation is the original Pinceler lemma, which is well known, showing that two inequalities expressed as parameters are the equation conditions A and B are equivalent. However, since the proposed method uses transformed parameters omega in the controller, which is expressed as inequalities that include the new parameter, which is provided by new Pinceler lemma. This yellow box is a closed-loop system in which a parameterized system and parameter-dependent controllers are expressed with different index I and J. So it shows the stability condition of the closed-loop system. You can see the orange box is expressed as a parameterized inequality by adding the system equations to these stabilization conditions. It is general expressions. In the conventional method, the condition that satisfies both index ij for diagonal terms and off-diagonal terms were used. In the proposed method, the entire parameter conditions was expressed at once. So, this page shows the examples using additional parameter condition in parameterized LMI condition. The condition number 1 represents the stabilization condition of the system, and condition number 2 expresses a parameterized expression of constraint of the membership function, that the sum of parameter is 1. So by combining the inequality and equality conditions, we can combine by using S procedures like condition number 3. So usefully parameter information of the system can be included in the LMI. When unaffine transformed membership functions expressed as omega equals alpha, zeta plus beta, the affine transformed membership function is used in the parameter-dependent controllers. we use different membership functions. It is expressed as a new variable w, which is obtained by transforming the existing membership functions, which with a constant alpha and beta. The reasons for doing so is that the constraint can take advantage of information. Actually, the parameter theta I and j, the difference value is bounded 1. But our proposed transformed parameter omega I and j is bounded by alpha because constant beta is eliminated. So we can reduce the upper bound. So difference between the members function is limited to the alpha. In the parameterized LMI conditions, the alpha included in the last terms as shown at the bottom of equations. The last term contributes a lot to relax the design condition. This is main key ideas. By using the ideas, we developed stabilization conditions for TS purge system. This paper is published in the IEEE purge system in 2018. From these phases, various applications based on our ideas are introduced. So we consider the TS purge systems, they generally formulated the control system. The parameter summation constraint is expressed as shown. And we consider the parameter dependent controllers. In here, psi is affine transformed with alpha and beta. So closed loop system can be expressed with index ij, theta, and psi. So by using our parameterized techniques can be applied. Based on the common reaffirm functions, we can derive the stability conditions using x dot terms. So we can derive the equality conditions. Differently existing method, we can use the full block pre-matrix can be applied, multiplied in the equations. So by combining the two equations, we can obtain the stability conditions with ij index. So by combining the reaffirm function and system information, so we can summarize as these equations. In the first term is I terms, and second term is cross terms. So in order to parameterize, we rearrange this cross term. So we can express by using alpha and beta, we can reformulate the parameterized inequality conditions. So in the simulation examples, we can find the improvement of simulation result when we consider this kind of fuzzy systems. Consider the fixed parameter 3a and how to enlarge the parameter b for satisfying the stabilities. Current existing result can increase the region of the parameter b within these values. But in our method, remarkably increase the regions. I cannot believe in the first, but after simulation, we can show the stabilized wells, and we can get the enlarged region, stabilizable region. So when we utilize some parameters variations, we can remarkably improve. The idea also can apply the sampled data stabilizations for TS purge systems. This work is published in this year's Journal of the Franklin Institute. So generally, the network control systems we consider periodic sampling intervals. So in the parameter also should be sampled. So in the different IJ index membership function, different affine transformed membership function are considered. So in order to handle the sampled data system, we consider Lyapunov-Krasovsky functions. After deriving some derivative of the Lyapunov functions, we can derive the stability conditions. In here, we can encounter these kind of the integral terms. This term can be found by using some integral inequality conditions. It can be described the existing vector. So by using some integral inequality conditions, we can find some stabilizable conditions. Detailed proof can be found in these papers. This page explains the integral inequality. So this complex term can be easily summarized by using existing augmented vector. So this theorem shows the stability condition. If satisfied this kind of the inequality condition, we can find that the stabilized condition can be reconstructed. The demerit of our proposed method is there are so many pre-variable, so it takes it has large computational burdens, but the control gain is obtained in the off-prime. In the inverted pendulum system case, we can easily apply the how to increase the sampled data. Sampled intervals. So we can make some TS purge models, and in these figures, the solid line means the original membership function for the system, and the dashed line is a fine transformed membership function. So original membership functions value have between the 0 to 1. But ours, the controllers, the membership function have reduced the range of the membership function. So we utilize this information like that. So we can obtain this kind of control gain. Actually, so we solve the TS purge stabilization problems. The gain becomes a similar gain, but in our studies, we can get different gains are obtained by using our affine transform technique. So this value shows our improvement. Even though the sampled time have 1.23, the meaning is inverted pendulum can be stabilized even though the sampling time have 0.23. Very long time can be stabilized. This simulation shows the successful stabilization well. Existing works just obtains within the 0.04. We improve about 5 times. This works also we can apply to estimated design in the static neural networks. This work also we utilize to design the parameter dependent gain. So it is called as parameterized Ruenberg type estimators. This work is published online in this year's neural network and learning system. Considering this static neural networks, we try to find the stability conditions for large slope bound and how to find the stability condition for time delays to increase the time delay. Left side is originals considered neural network systems, and some constraint. We want to design parameterized Luenberg types estimators. In here, the gain is parameterized. So when we consider these examples, which is very popular used, by comparing the H infinity performance for different values, lambda is maximum upper bound of the nonunities. When increase the numbers, the H performance is increased, but our result have the supers, the dense, the existing works. Also, so the H infinity's performance can be compared with the different value of time delay. So our proposed method have this is value is H infinity performance. So even those large time delays, we can get improved H infinity performance. So we can reserve each trade-off. This is the second example. So this example also is well known the benchmark problems. So we can get smaller H infinity performance compared with the existing recent published paper. Now, so I will conclude all of the works. We propose some improved design method for parameterized nonlinear system, TS-PG, or linear parameter bearing systems. In order to relax each constraint, nonlinearities, and maximum time delays, and maximum sampling intervals, to improve the H infinity performance, we apply the applying parameterized techniques and using sampled weight parameters. Also, the immeasurable weighting parameters can be applied in our techniques. By using the benchmark problems, our superiorities were verified. That's all my presentation. Thank you for your attention. Do you have any questions?
Oh, it's really a good result and interesting.
Thank you.
In quasi system.
Yeah.
In 2021, there is a good result in TNN. Yeah. I will after this report, I will download the paper to study.
Yeah. You can download it. If you need some example code, I can support you.
Okay, thank you very much.
Yeah.
I will introduce you another prof in our college, Prof. Liu.
Yeah.
And Prof. Liu.
Hi, can you hear me?
I can hear you.
Hi, Professor.
Yeah.
Sorry, I don't have a camera at hand, so I just use the voice.
No problem.
Okay. Yeah, I listened to your talk and find it's very interesting. And the fuzzy algorithms seems very powerful.
Yes.
A lot of problems. Also, I noticed that you have some projects about the robotics, such as the Sawyer, and some vehicles. So, have you applied these methods, these theoretical methods on these platforms?
We use in this project we use sliding mode control technique to estimate the external pulse. To predict the external pulse, there are several methods, but actually, Sawyer robot have 7 joint link. So to estimate each joint external pulse, we should apply the sliding mode control techniques.
Okay, so you used some other control techniques, not this fuzzy
No, not used. Just based on the robot dynamic models, we can apply the nonlinear dynamic problem.
Okay. I see. Yeah. Okay. So actually, I have some other questions. That is, if when fuzzy control approach is applied, so you have studied the sampling period, different sampling period, and
sampling interval.
And the system with time delays.
Yes.
So is there a bound, explicit bound for this time delays or the sampling time intervals?
Yes.
That this the fuzzy control approach can handle.
Yeah.
I didn't see this bound in your presentation.
Okay, in order to find the stabilization condition for the sampled data systems, we should consider some this kind of reaffirm function is called as roofed function. It is based on the common reaffirm functions. We should consider this kind of reaffirm function v2 and v3. This function is become 0 at each sampled time tk and tk plus 1. So based on that function is called as roofed function, which is developed recent years 2018. So various researchers utilize that kind of reaffirm functions. We also utilize similar techniques. But we utilize new upper bound for the inequality conditions to estimate the integral term. Actually, this integral term is expressed as some vector combinations, so it is not easy to extract some zeta to formulate it in LMI. So by using some useful lemma can be applied. By using this lemma, we can easily find some upper bound using some given augmented vector. This is key techniques. In here, we also this is general straightforward schemes. In here, we also utilize some affine transformed function based on the modified pencil lemma. Actually, the system can be expressed as linear combinations index I and j. So when we use some different membership functions, we can utilize the constraint of the new parameter.
Right. So use your controllers. The sampling time interval can be longer.
Yes.
I can see in your simulation example.
Yeah, in the example.
I mean, I mean, do you have a mathematical upper bound for the sampling period?
Yeah.
The sampling interval.
The mathematics, the upper bound of the sampled time is cannot fixed because our problem is not the stability problem. By using some controllers, we can increase the sampled time.
I can see that from your simulation example.
This simulation is this simulation conducted with this largest sampling time.
I was just curious about if it is possible to characterize them. Maybe it's very difficult.
when we utilize this kind of control gain for this kind of sampling intervals, we can find this stabilizing wells simulation result. So first time, so we cannot believe this kind of result, but this is the correct result.
Yeah. Inverted pendulum are very time critical systems that need very fast sampling.
Yeah. It needs a very fast sampling, but we can find some systematic control ways based on the theory.
Okay, thank you.
Yeah, thank you.
I don't have a question.
Okay, I have one question about because I'm interested in your model predictive control. In the first, maybe please put on your slide before.
What is the numbers?
Maybe there is a
mobile
structure.
robot.
Yeah.
In this.
In
this works, we utilize MPC.
Yeah.
Yes.
And I saw the controller is a composite controller, including the MPC, and another controller is what is it?
Yeah. You are so smart. This is a very important concept. Actually, when we try to solve the stabilizing problem to achieve to arrive at some position, MPC is enough. Is right?
Yeah.
And in this problem, so we should make the solve the tracking problem. So based on this control inputs, we cannot solve the complex motion. So in order to produce some based on the LiDAR make some another control inputs to follow or avoid the obstacle. So we add on another control input is generated from the LiDAR data.
I see.
So this is the concept is similar with when we considering nonlinear systems, we should utilize operating point control input U0 plus Kx. So it plays a role as operating point shift.
Yeah.
Can you understand?
Okay, I see. Yeah. It means the UT to guarantee the tracking errors in a little area.
Yes.
And the MPC to treat with the constraints.
MPC is MPC is a very powerful tools to tracking some trajectories, and another one is it is helpful to handle the constraint. So in the mobile robot case, we have several the environment constraint. So by to solve the optimal control inputs problems, we should consider some several constraints. So we apply the MPCs based this kind of the control design method is well known. MPC general MPC method is applied. In years, the parameter every parameter is applies to obtain the control input.
And the MPC's form is described by, and this plant is continuous.
Yes.
How to?
MPC can obtain from each sampled state. So when we calculate the control inputs, the different parameter, update parameter is applied in here. So we can calculate it easily. Because this problem is solved by using leader following model. So in here, theta is utilized using some leaders velocity. We use directional velocity and angular velocity is utilized in theta parameter.
Yeah, okay, I see. Thank you.
Yeah.
It's really a good, interesting topic and project.
Yeah. Nowadays, I want us to combine the control theory and AI techniques. The control theory cannot solve the various nonlinear motions to imitations or the not easy to apply the industrial field. So nowadays I want us to combining to basic control theory and how to utilize learning mechanisms based on the learning and reinforcement learning. So next time, so if you give us some opportunities, I will introduce another learning and control technique.
Okay, I will.
Yeah.
There are some questions by some other students. Okay, we will end today's report, and thank you, Prof. Lee. It's really an interesting report, and we will meet next time. I will invite you.
Yeah, thank you very much again. See you next time. In online or offline is okay.
Okay, have a nice weekend.
Yeah. Thank you.
Yeah, actually, I'm interested in your next talk, the learning-based control.
Yeah.
Yeah, I hope to see you next time.
I will study very well.
Yeah.
Okay.
Okay.
Yeah.
Okay, see you.
Yeah, see you.
Bye-bye.